So yeah, I'm just going to dive right in. This was kind of more or less already covered, so appreciate that. I forgot that I sent a bio. My careers span distributed systems and a lot of container orchestration, cloud native stuff. It's been fun seeing some of you here that I know from the Apache Mesos days. Now I've been spending some time thinking about higher in the stack, building actually applications on top of these container orchestration frameworks, ways that we can make that easier. So that's what I'm going to talk about today. Because the reality is that building distributed full stack apps using microservices and lambdas is challenging. It's great for me to be able to say that because most of my previous talks were all like, hey, you should be building your apps using microservices and lambdas. And I think, I tried for this presentation to isolate sort of two things that I thought really drove how we thought about this new programming model. And the two things that I captured were one, what I call the scale paradox, which is that when we're thinking about building modern cloud native apps, we really want to embrace being distributed so that we can do work in parallel and we can be more fault tolerant, but we don't want partial state updates. And I'm going to talk in more detail about exactly what I mean about that in just a second. And then the second one is what I call the retry paradox, which is that in the face of failures, we're making all these calls. Yes?
You're blocking the...
Oh my gosh, that makes sense. Yeah, thank you. Perfect. In the face of failures, like a network failure, we want to be able to retry calls, but we can't. We might not be able to do that if those calls actually have effects, because we only want those effects to actually perform once, right? Okay, so I'm going to talk about these in a bit more detail. Now, listen, microservices have a lot going for them, right? Modularity makes it easier to understand, modify, and test your specific parts of the app. It gives teams engineering agility because they can operate and deploy their software independently and autonomously. You can encourage technology diversity behind well-encapsulated APIs. People don't have to know what languages you're using. And all that makes it easier to scale the application and easier to scale a company. So there's a lot going for modularity and composition and all that stuff. But they also have their challenges. And so to really talk about those challenges, I want to start with this example, which is your standard e-commerce checkout. And when you look at this code, there's a lot really to like. Independent teams can clearly own a bunch of these different services: the cart service, where you might be getting the items and storing the items; the shipping service; the payment service; the emailer service; so forth and so on. But there's a really big possible problem with this code. And that is, what happens if there happens to be a failure after, say, we've authorized the charge and before we've shipped the order? Right? What happens if I'm writing software like this? Free money. Right. So, the reason why people write a lot of code like this that runs up as, say, lambdas or microservices is because oftentimes the developer's intent is that all of this actually executes atomically. And of course, if, say, on the front end there happens to be a failure and they want to retry, that it only happens once, right? That it happens idempotently. So there's really kind of two camps of people when I present this example that I feel like the entire audience falls into. One camp is the people that are sort of like, Ben, why did you show that example? Nobody would ever write a microservice like that. We've all learned that lesson, right? And then there's the second group of people that are actually thinking to themselves right now, oh my God, do I have this bug in my own code? And most of us fall into that second camp. And one of the reasons for that is because this checkout example I literally took directly from Google's microservices demo. This is actually just their demo. So everybody starts with a broken model. Okay, and these are real bugs. We see these things all the time. I have a habit of trying to take screenshots when they occur. This is me actually trying to deposit a check. I got a failed to deposit check, OK, or try again. I was trying to deposit a check. Naturally, I clicked try again. About 24 hours later, I got this email. We're unable to process your mobile check deposit. My 219 check deposit. I gave them a call, and they politely accused me of bank fraud, trying to deposit a check twice. I just sort of laughed and said, yeah, I know it happened. We retried. It wasn't idempotent. Trust me, I'm sorry. I was not trying to commit bank fraud for my $219. So a lot of our code that's executing out there is completely inconsistent. And many of the people that have run into this in anger, these problems in anger, they've tried to fix it. And a lot of companies have moved from kind of an inconsistent world into an eventually consistent world. And they've done that through what we like to call the rise and ubiquity of queue-glued software. So we've realized that we can't just make these RPCs. We need to try to figure out a safer way to do it. So instead of just making the calls we want to make, we write everything to queues, we read from queues, we make sure those queues are durable, and we're in a good place. This leads to an inversion of control, callback hell, business processes scattered throughout the code base. There's a reason why the modern languages that we use all have async await. It's because that's the programming model we prefer, but in the back end, we're still just gluing everything together with callbacks. It's especially interesting to me that where most of the apps that we're building are living in is eventually consistent, given all the work that has been done in databases, making it a strongly consistent world. Our applications are eventually consistent due to queues, event sourcing, durable execution might be a strategy you're taking to at least solve the callback hell problem, but you're still eventually consistent, even though the databases you're writing to are strongly consistent. All right, so for all these reasons, this is one of the reasons why I think lots of really smart people tried to tell everybody, hey, microservices, this is not the architecture you're looking for. And the conventional wisdom became that you should only adopt microservices or lambdas. Anytime I say the word microservice here, I'm implying lambdas as well. When you graduate off of monoliths, when your product and company are scaling like crazy, because that's the perfect time to completely re-architect and rebuild your application. Okay, so question is, can we do better? And after spending a bunch of time working with a bunch of organizations that were transitioning to microservices lambdas, we decided to spend some time thinking about it. And I would like to talk to you today about a new programming model that we're trying to create to do better, to solve these problems. Okay, so the Reboot programming model. So this is a systems meetup. So I'm going to go pretty deep and talk about the programming model, talk about how it works, how things were designed. And the goal of this presentation is that hopefully you walk away thinking a bit deeper about what should be the best programming models for building full-stack distributed systems in the future. All right, so the Reboot programming model. So what is it? So it's similar to actors. Reboot's similar to actors in that we encapsulate behavior, state, and communication into a single abstraction that we call a durable data structure. Now, unlike actors that are oftentimes stateless, they just have their memory, they just have memory, these are durable. These entities actually have durable state, and you're going to see some examples, okay? Instead of passing messages like actors, you call methods. So it's RPC-based. But these methods have a well-defined semantics for how they compose together safely. This is really important. This is what I'm probably going to be spending most of the presentation on. And so instead of thinking in tables and rows in a database for your durable state, you think in terms of durable data structures that end up being distributed. And you're going to see some examples, okay? So this is the basis of the programming model. All right, so let's dive in. Durable data structures. So to start, you have to describe these data structures. Now, I'm going to be showing you actually some code from Reboot. But again, it's the programming model that I think is most important here. In Reboot, you actually describe those data structures, the schemas and the methods on the data structures using an IDL, an interface definition language. And the one that we've used so far is protobuf. So imagine we're building something like a bank. Okay? We've got things like accounts. So you describe your account type. You'd imagine it have things like the name, the birthday balance, and other things. And then you also describe the methods that you can call for an account. Okay? Things like doing a deposit, doing a withdraw, getting the balance, opening. And what's really, really important is for each of those methods, you annotate them with the type of method that they are. Okay? And the methods can either be readers, writers, transactions, or workflows. And depending on how quickly I speak or how curious the audience is, I'm going to talk about readers, writers, and transactions. I might not get to workflows. Okay? All right. From that, you actually have to implement the code for these different durable data structures. If you've ever built anything with gRPC, I'm sorry, no, I'm just kidding. If you've ever built anything with gRPC, this looks a lot like gRPC. This is kind of gRPC on the left-hand side. On the right-hand side is how you'd implement the code for a count. Okay? I'm going to be showing Python examples. So this is Python code. All right. Okay. So let's dive in. Just real quick. So the basic idea is that you can construct instances of these data structures. So I kind of glossed over it briefly, but we actually made open a constructor as well. So I can construct an account. I can give it an explicit ID if I want. I can get a reference to an account, and then I can call the methods on that account, just like I'm calling functions on types. Okay? In particular important, when I call those methods, I have to pass a context. Okay? And this context becomes really important for how we provide safety in the programming model. Okay? All right. So let's dive in. Readers. Okay, so how do readers work? All right, so readers take a reader context, which we'll talk about in just a second, an immutable snapshot of the state. So unlike, say, if you've worked with something like gRPC before, one of the big differences in this programming model is you actually get past the state. That's the state of your instance. Okay? And then you can go ahead and you can read that state. You can do whatever you want with a state, but you can't, if you make any updates to that state, it's not persisted. Readers are only reading. Okay? Now, important, readers get this reader context and can only make calls to other readers. Why? Because getting back to the problem we were talking about earlier, we're trying to avoid partial state updates. So we're trying to build up a programming model that guarantees safety. And so readers can only call other readers. Okay? All right. And then, of course, they return a response. All right. Next, programming model, writers. Writers, like readers, get past context, state, and request. But in this case, writers get a current state and are able to actually modify the state directly. And because of that, I forgot to say this, readers can be executed concurrently because they have a snapshot of the state and they're not making any changes to it. Writers are executed serially, one at a time. They can mutate the state, and when the function returns, that state will be made durable. Okay? But they can only call other readers. Why? Because again, we want this atomic no partial state property. So writers can only update their own state, but they can call readers, which we know inductively can only call readers, and therefore there'll be no other state updates made throughout the system. Okay? All right. And then they get past a writer context. Okay, so how do we enforce safety? So I just want to pause. I want to talk about the other methods, but how do we enforce safety? Okay, so first, the two safety properties we need to try and enforce is that you only call allowed methods. Right? So far I've said readers can only call readers and writers can only call readers. So how do I enforce that? Well, we enforce that because, as I said, every single call that has to get made, you have to pass the context. And you can only call reader methods by passing, if you have a reader context and you go to call something, you can't call, say, a writer method or a transaction method because you have the wrong context. Okay? We can test this with a type system. So we can check this reliably before we even run the code. If you choose not to use a type system, we can also fire runtime exceptions if you give us something of the wrong type. Okay? All right. The other safety concern we want to check is that there's no other side effects. And we don't technically have to do this, but the goal is that actually the way you've written your code is that the only effects that occur are effects within the system. And so we want to make sure that you're not actually doing any other side effects. Because by all means, maybe in a reader, you can choose, you won't be able to call a writer, but perhaps you're going to try to reach out to some other external internal system and make some side effects. So, this fits squarely in a lot of PL research, people trying to come up with perfect programming models to figure out how to avoid people writing code that have external side effects. We don't do anything like that. We do a little bit of type system stuff here, which helps. But the way that the programming model tries to improve this is during development, when you're running your code, or if you turn on a flag, we just execute every RPC twice. You're going to find out really, really quickly if you happen to be calling out to some external system in which you're performing a side effect. This was not our idea. For anybody that's actually built a React.js application, this is something that they do in strict mode. React.js is, I think, one of the most successful pieces of tech to get programmers building in a more functional way without all the heavy-handedness of type systems, just doing really clever things like this, where they're just doing things like executing your functional components, your components in React twice, so you figure out very, very quickly if you're doing something wrong. OK? So we do a pretty good job. We do a less good job, but still good enough for practice. All right, that's it. All right. Now, one of the big powers of having side effect-free readers is that enables us to introduce reactivity as a first-class primitive in the programming model. OK, so I'm going to transition here a little bit to from the account to a bank. So you can imagine a bank has one of the methods called account balances, which is a reader. This is the implementation of account balances. What does it do? It reaches out to some other durable data structure, a list. From that other durable data structure, the list, it gets a page of account IDs. We pass -1 to just get the last page, so the most recently accounts that have signed up. Then we loop through all those counts, and for each of the accounts, we call and we get their balance. We aggregate that all together in some dictionary, and then we return the dictionary. OK, so that's what the function's doing. Now, where does reactivity become really powerful? Reactivity becomes very, very powerful where we can expose this up all the way to front ends. OK? So thanks to that IDL that we originally wrote, what you can do is we actually generate code that can be used directly by React, or could be used in other HTTP fetch-like scenarios. But in the React case, we generate code that allows you to actually call into these reader functions such that any time that state changes that would change the result of this reader function, we can re-execute it and propagate that all the way back up the stack. OK, so in particular, when I call into my list, if some other account gets added to the list, because we're only doing reads, we can propagate up that read knowing that we can re-execute this. Or if balance changes, we can do that. We can propagate this information all the way back. And then again, in a reactive setting like React or any of the other reactive front-end environments, they can basically get this information and re-execute. So we're trying to push reactivity beyond just the front end all the way into the back end as well. OK? All right, and again, we get this because the readers are side effect free. So we can perform that. OK. OK, let's keep going. Next part of the program I want to talk about is transactions. So readers and writers, great. But at some point, you probably want to write a function that needs to update state in multiple other durable data structures. So how do we do that? We do that with transactions. So you mark a method as a transaction. This is bank. This is kind of your canonical transaction, right? I'm doing a bank transfer. I'm withdrawing from one account. I'm depositing into another account. Okay? Transactions take the current state, just like readers and writers, but that state can be mutated just like writers, and they can call everything. They can call other readers, they can call writers, and they can call transactions, because there's extra heavy lifting going on to make sure that all the state that's being updated throughout everything that's being called for a transaction is done atomically. Okay? And that's really the key. The key is that this is the partial state update we want to avoid. We want to avoid that we do a withdraw and then there's a failure and we don't actually do the deposit. Now, what's really, really interesting and powerful about this programming model is when you give a programmer something like atomicity at the function level, you can actually write code very differently. In particular, we'd probably withdraw and deposit at the same time. So even though there's more machinery that's happening to actually make sure that this is executed atomically, we can run the code faster. We can eliminate an entire round trip time. And you can imagine, thinking back to that checkout example, you can start to look at the actual data dependencies you have. And in the checkout example, almost everything can be done in parallel. You can eliminate something that was, say, 8 round trips to 2 round trips. The first round trip, get the card items. The second round trip, do all those things in parallel to everything, get the response, go from there. OK, cool. Yeah, I've been kind of saying, like, I've had a couple slides where I've forgotten to mention it, but again, what's really powerful about this is the code that people are writing here feels very imperative. It feels very imperative locally, but the experience that you're getting throughout the entire application is very functional. And this one I put kind of squiggly imperative because the minute you start doing some things in parallel, there's some open questions there. All right, so what about this whole retry thing? I kind of mentioned it when I was talking about the checkout example that, what happens, how does the front end actually figure out how, if it can retry checkout, should it retry checkout if there's a failure? So to solve that problem, we just decided that the programming model should have idempotency built in, 100% built in. Okay? So if you did want to write transfer and you in fact wanted to say, try and do withdraw and deposit, and check to see if something failed when you were doing that because of a retriable error, like say a network failure, you could just explicitly do that if we just make idempotency a built-in thing. But what's interesting here is that for the most part, you'd really want to push this up to the client. And so the same thing, idempotency for the generated code as well here is completely built in so that these transfers can be retried from a client completely safely. No more like, don't hit the back button or the refresh button. Hit it all you want, because if we try it again, we'll make sure that it only happens once. Okay? And there's a lot of machinery to make that work, but the trade-off from a programming model, I think the juice is worth the squeeze because it dramatically simplifies the programming model. Okay, all right. So just a couple more slides, and then I'll take some questions, and if people have questions about some of the other parts of the programming model, I got some backup slides. So again, kind of getting back to that original scale paradox, you want to embrace being distributed, but at the same time, you want a simple enough programming model. One of the things that we're really trying to strive for with Reboot is that you can think of an application as just being a collection of all the code that implements all of these different data types and their methods. But the runtime can actually be what's responsible for deciding how to distribute that code based on the data. So if you have two banks, maybe that they run on two different machines, but if you have 500,000 accounts, maybe those run on 100 machines. But you don't care. It feels pretty monolithic for you that you're just saying, hey, here's my code that implements this stuff. As these durable data structures get created, please figure it out. Okay? Now, one of the other things that that really excites me about this model as well is we talked a little about list. List was one of those other data structures that we used. There's an opportunity for people to actually create their own durable data structures and share them with others where it's as easy to pull it into your application as literally like, hey, here's the code that I need to run. So you don't like our list? Go build your own. Share it with other people. You want to implement a distributed B tree because it's important for the app that you're building? You could put it up on GitHub and other people could download it and run it. And it'll run in a distributed way based on all the primitives that I talked about for the programming model. All right. So, this monolithic experience, but then scaling and running like applications, this is just kind of a little graphic talking about what we mean here, right? As you create more accounts, those accounts can be partitioned and spread. We can route the requests for particular accounts to the necessary places. Okay, so you can actually experience this if you wanted to play with Reboot. You could totally try it out. We've got a tool called RBT. It's an old slide. My bad. We've got a tool called RBT. And you can try it out. Like you can actually run locally, and you can create like 32 partitions if you had a 32 core machine, and you can like actually see you running hundreds of accounts across a whole bunch, all your CPUs. You can make your computer heat your room as it takes advantage of all the resources. Okay, all right. So I'm at like 24 minutes, so I think I'm gonna cut it there, and I'd love to answer any questions that folks have. Okay, cool. Questions? Yes, sir.
I think this is awesome. It's very like, I don't know, Microsoft Orleans meets Captain Proto meets, I don't know, reactivity. It's great. What's the scalability and isolation properties? Like you touched on databases solve a lot of your data scalability where like writers are serialized, and is it like per object and then cross object transact? Yeah, how does that work?
Great question. Yeah. So if you've spent much time in this area of research, there's even research that dates back even farther than Orleans and all those things, like from Barbara Liskov and those folks. I think one of the things we actually were trying to do specifically with the differentiation of readers and writers was for performance readers, was for scalability readers. A lot of previous systems have basically just dropped transactions as the be-all hammer to execute every single function, and they're the expensive ones. Readers are actually very cheap, and 99% of the apps that I think people build, getting a snapshot, returning the read is sufficient. I'd be happy to go into deeper about at least reading your writes, which we make sure happens, right? But that's like 99% of the time, that's sufficient, right? Writers, I can't tell you how many people, when we first started talking about like how to build apps with Reboot, they get by, their first apps never touch a transaction. Most of the first apps they build are effectively just row updates, which is effectively a single instance of a durable data structure. They don't need transactions till later. So performance is significantly better by exposing those two as explicit primitives, and kind of as a programming model leading people to trying to use those things first, because transactions are more expensive. It's two-phase commit. There are some tricks we can play, like architecturally. They're very interesting commits, and as I did mention, sometimes you will write your code differently, which will be dramatically better in performance. But to be clear about the isolation, writers are atomic, so one writer executes at a time. Readers just have a snapshot. Transactions are obviously atomic. I think that there's more opportunity to push the programming model farther, specifically for writers. There are some writers that you might say, you know what, the mutation that I'm doing, the update that I'm doing is actually associative and commutative, and I do not need to try to execute in a serialized way. It will converge. Those can be executed in any order. And so we even have ideas of being able to let you say, hey, this writer, the state, it doesn't return state. It returns something that ultimately will be incorporated in an associative and commutative way. And then you basically give somebody a CRDT-like primitive, but they get to write this like imperative function where they're doing stuff. I don't know if I covered all the things there, but yeah, cool. Yeah, more questions?
Yeah, so I want you to clarify like the sort of problem statement here. So when you have like a card example, like one of the problems you can have is that you could send two emails, right? You do
all the time. Happens all the time.
Right, so,
we get two emails all the time, right?
One is kind of like retries on kind of non-idempotent systems, right?
Yeah.
Like that's kind of a core problem
Yeah.
that's there. And you really can't solve that? Like, is that impossible to solve because...
I'm so glad you asked that question. Yeah, so like one of the big questions is like, okay, this is great when this is all within my own system. But what happens when I'm using like some external email service that I'm trying to send to, and I've got external effects? What do I do then, right? So the insight is that almost all third-party APIs that we're actually calling out to do not support any kind of rollback, and many of them are not compensatable. And those are the two things you need to do if you want to be able to deal with not having partial state updates. So the conclusion for Reboot is that you, for the external systems, will not have strong consistency. The best you can most likely have is eventual consistency. So what do? Well, you could dry run that external mutation. Most emailers will let you do that. They let you make the API call and say, return to me if I did something wrong. Like I gave you an address that you can't route to or blah, blah, blah. So by all means, during the transaction, I could do that. I could at least feel really, really good. And then I can execute the effects after the transaction is committed. Now, there's a whole cool way in the programming model that we actually do that, where we allow you to basically schedule the execution of an RPC later that will actually perform it. That scheduled RPC is actually that last type of method that I talked about, workflows. They are the least safe. They are the ones that there is no atomicity guarantees. They're the last hammer you'd want to reach for. But they allow you to basically write code in this idempotently converging way where you might be calling out to an external system, and the best you can try to do in those circumstances is converge on some kind of outcome. But within your own internal apps, if you can make things strongly consistent, why wouldn't you, right?
The other part of the problem statement that I'm wondering about is, like, if it is all your app, then if you had one database, you could just push like the updates down to one big SQL statement that kind of does everything at once.
Totally, it's called a monolith.
Right. So the idea here is that this is sort of a programming convenience, so users don't have to do that.
Yeah, I mean, also you want to distribute this possibly across a bunch of different machines, right?
But then at the end of the day, like, the actual transaction writes have to happen in like a batch to whatever durable store you're using. So, like, I guess this is like a nicer way of doing what you're going to be doing anyway.
Yeah, again though, if you, the reality is most people are going to have separate independent services that they're building that make up this whole thing that are all communicating with one another. Like you don't typically just have a single database. You have many instances of databases if you're following the microservices path. If you're following the monolithic path where you just have a single database and yeah, you're calling locally on a single machine when you get a request and collecting up all the things you need to do and turning it into a big SQL statement that then you fire at the database and get things done transactionally. Yeah, you can keep doing that, but we're trying to provide a programming model that gives you the feeling of kind of just making local function calls, but they might be entirely distributed across a whole bunch of resources depending on how things are running. I wanted to also clarify, or not clarify, but one of the things that I think would be really cool is while today external effects might have to be done eventually consistently, wouldn't it be amazing if some of these other APIs could literally just provide a reboot style protocol? Like if that could be a future, because then I could call into Stripe transactionally. So it's one of the reasons why I'm trying to present this is get people to think more deeply about the idea of introducing more new programming models that would allow that kind of composition safely, so that we wouldn't have to do this. We could literally just call to Stripe. Stripe could do whatever it wants for its own internal pieces. Okay. Other questions? Yeah.
One thing that was not at all obvious to me, you mentioned that you have this mechanism to basically send updates reactively to a front end.
Yeah.
And like, obviously there's so much machinery going behind the scenes, but I can't figure out a mental model.
What is that machinery? Yeah.
Like what, just if you give me a sense or something.
Yep.
Like,
It's what most people have just implemented. We just implemented it once. WebSockets.
okay.
A query gets made over the WebSocket. When there's any updates, we propagate that information back. And basically, it's the same thing happening between the services themselves, like in the example that I gave. The WebSockets are specifically coming from the browser, just to be clear.
Okay.
On the back end, these calls, you can think of it as like a long-lived subscription.
Yeah. But that's all in the implementation of these types, I guess. You don't have any like metadata services that are. There's just like a programming model, I guess, right? It's not. There's no external like management of the state in terms of. Does that make sense?
I'm not sure. Like in terms of like the updates of the actual, like when you do a writer update, like here when I do state.bounce. This is actually being persisted, like in the implementation that we've built, like we're persisting that in a database or in a file system, or a combination of the two. So the state is that the question?
Yeah, kind of, yeah. Thanks.
Other questions? Or call it?
Yeah.
Cool, awesome. All right, thanks so much.
It's like,
Thank you, Ben.